Welcome back to Old School Math. Today we're going to be talking about the average rates of change in a function. Now, this goes back to Algebra 1 when you learn how to calculate the slope of a linear function or the rate of change of a linear function. And you did that by finding its slope. And you probably remember this formula, m equals y2 minus y1 over x2 minus x1. So in this you had the ordered pairs x1, comma, y1, and x2, y2. So this x1, goes here, this x2 goes here, and vice versa. And we know that these 2 points are more or less interchangeable, right? Now, in this equation, you found the slope by using these points and just plugged it in and simplified that fraction. And we can do a similar thing with a function that's not linear. We use the average rate of change to find a nonlinear rate of change, or where the slope is not constant. That's the main difference between this slope and our average rate of change formula that we see here. It's just we use this when it's not constant, and we call that an average. Similar to what you would say, my average speed for a trip would be 60 miles an hour, but most of the time I was driving 70 miles an hour, but I had to stop for, get gas and use bathroom and get snacks and that kind of stuff. So that's the only reason we call this an average. It's not instant at any time, and it does change. So in this equation, a and b are just x values for the function, and f of a and f of b are the function values at fb and fa. Basically, all that's saying is those are the y values. So really, this is pretty much the same equation as the y value at b minus the y value at a over b minus a. That might be a little bit more helpful. And instead of saying just b and a, that's the x value at point B minus the x value at point A. So you can use this equation as well. It's the same thing, but it keeps you in reminding you that you put your y's on the top and the x's on the bottom. And you do have to put those in the correct order. Now we'll do a couple examples together to see how this actually works. So this says, look at the average rate of change for the interval 1 to 4. So these are the x values, where x is 1 and x is 4. For this function, x plus 2 quantity squared. So we know that this would be a shift to the left 2 units. So my parabola, and I'm going to just sketch it in real quick here. It's going to look something like this. Probably not that crooked. But let's go ahead and graph this in the calculator. And I'm going to show you a trick in here, okay? So we'll put this in the calculator, x plus 2. And you can use decimals for this as well. And we'll look at the graph. We see that it does shift to the right 2 units. And then if you go to the table, you can actually find those values really quickly without having to do any substitution. So you get the point here, 1, 9. And I'm going to write that down. And then we also want the point where the x value is 4. So we'll go down and we get 436. All right. So now what we're going to do is substitute these into this formula up here, or basically just find the slope between these 2 points. So if we do our y2, that would be 36 minus 9. So subtract your y values, and keep in mind what order you did this in. Then we'll do 4 minus 1. And then we'll just simplify this fraction. And I always like to do this by hand if I can. So 36 minus 9 is 27. 4 minus 1 is 3. 27 over 3 is 9. So that is my average rate of change for this function. Now that tells me between the values of 1 and 4, this goes up by an average of 9 each time. We see between 1 and 2, to jump from 9 to 16, that only goes up by 7. We see between 16 and 25, that does go up by 9. And then between 25 and 36, that actually goes up by 11. So if we average those out, we would get 9. In this next one, we've got negative x plus 2. Negative square root of x plus 2. So let's do it. Let's put this in our calculator. Negative square root of x plus 2. All right. We can graph it, and we want to go between x equals negative 1 and x equals 3. So if we look at our table here, and we should see that this should be a negative rate of change because we have a negative slope in here, or it's sloping down. So we'll go in here. We see some errors, and that's nothing to worry about because that should be pretty common in a square root. And so we get the point negative 1 for x and negative 1 for y. Keep in mind, these are our x values. And then for 3, we get something weird. 2.23 I'm going to call it negative 2.236. If you want to give a perfect radical, that's fine, but I think a decimal on these is more than okay for this example. So then we'll do the y2 minus the y1. We'll do our negative 2.236 minus a negative 1, which we know that that'll turn into a positive. Minus a negative is always positive. Then we'll do 3 minus negative 1. And again, that minus a negative turns into a positive. Okay, so let's simplify the top here. If we do negative 2.236 plus 1, that would be negative 1.236. And then 3 plus 1 is 4. So let's go back to our home screen and let's divide this out and get a nice decimal. And we get an average rate of change of negative 0.309. So on average, each step, this is changing values between negative 1 and 3 of 0.309. Now this value would change if we had a different interval for this graph. And then let's look here, x minus 1 in absolute value plus 3. So absolute value, go to math and then number. We're looking at the abs and then x minus 1. So that should be a translation to the right 1 unit. Plus 3 will translate it up 3 units. And we see our absolute value graph, okay? And I'm going to sketch this one in. I forgot to do that for the square root, but that's okay. So this is going to do something kind of like that. All right, so I've got my absolute value graph, and we're looking at the interval from 0 to 2. Now, one thing that we'll notice when we look at this interval from 0 to 2 is it goes down and then it goes back up, right? We have a change in our value there, okay? So let's look at our values for this. Let's go back to our table so we don't have to do any hard thinking. We get the 0.04 and we get the 0.24. Now the thing with this to notice is that the 0 and the 2 again are our x values. All right. So we'll subtract the y, so that'd be 4 minus 4. And then we'll do 2 minus 0. So when we do this, 4 minus 4 will give us 0 over 2, or an average rate of change of 0 for this function. Now, why is my average rate of change of 0? It does change values in here, right? But if we look at this on the graph, at these 2 points, we could say, well, you know, if this is a distance versus time graph, maybe you're looking at it in a physics perspective, maybe we're walking backwards at some rate and then forwards at the same rate. And we end up at the same place there, right? So that would be a good kind of real world example of why this is 0, right? You traveled backwards and then you traveled forwards, and you did those at the same rate and ended up at the same spot. So it's just the equal time on both sides of that point. Now for the rest of the absolute value, if you did some interval in here, we could find, well, the average rate of change is essentially your slope. So you're not really doing anything new there, right? So the big idea between the average rate of change, to kind of sum it all up, is that you're finding the slope for a between 2 points that would be nonlinear. And if we look at this a little bit more closely here, between 1 and 4, we would see this parabola curving up pretty steeply, right? And so we would say, well, it's not exactly a straight line, but it is kind of straight, right? It's a lot straighter than the whole parabola overall. So if we say, okay, the average rate of change is just a line between these two, and it's the slope of that line. Guys, thanks for watching this video. Let me know if you have any questions, and as always, thanks for watching Old School Math.